so we just talked about oxidation reduction reactions, and we can use that kind of framework to understand nutrient cycles in ecosystems and biogeochemistry. So this is kind of a diagram showing a generalized nutrient cycle, taking an organic compound and mineralizing it, basically remineralizing it, turning it into a reduced inorganic compound, and then oxidizing it, turning it into an oxidized inorganic compound. Now, when things move in the blue part, in the upper part of the diagram, along with potential energy, that is, those are oxidation reactions, and they're moving with potential energy. Okay, so all of those circles are moving with potential energy. In the bottom part of the diagram, in the brown part, if they're moving in the opposite direction, they're moving with potential energy. So taking an oxidized inorganic compound and reducing it, turning it into a reduced form, that's moving with potential energy. However, see how that arrow going from organic compound to reduced inorganic compound is going against potential energy? So things can happen against potential energy, but it means that other inputs of energy are required. And so this is just a nice way to think about it. So when things are moving to the right in the top part of the graph, they're going with potential energy. And when they're moving toward the left in the bottom part of the graph, they're moving with potential energy. So with that in mind, we can look at something like the phosphorus cycle. Okay, so things like particulate organic phosphorus moving into dissolved organic phosphorus, moving into phosphate. Those are all oxidation reactions that are moving with potential energy. The bottom part, we have things though moving against potential energy, other than assimilation, which goes from phosphate into particulate organic phosphorus. That's like uptake of phosphate into an organism. Those other things moving in anaerobic environments are going against potential energy. So things like excretion and using phosphatase in the anaerobic environment. Here is a picture of the nitrogen cycle, probably the most complicated cycle. We'll spend a little bit more time talking about this in other weeks. But again, you can see that mineralization going from organic nitrogen to ammonium. That's an oxidation reaction. Ammonium to nitrite is called nitrification. Nitrite to nitrate is nitrification. And then in the other direction, going from nitrate to nitrous oxide and nitrogen gas, those are on the denitrification pathway. Nitrogen gas to nitrogen fixation, that's a reduction reaction that's going with potential energy. But organic nitrogen mineralization to ammonium in a reducing environment, that would go against potential energy. And yeah, so there's a whole variety of chemical factors that are considered pollutants, things like acid rain, we talked about a little bit, acid mine drainage, heavy metal pollutants, organic pollutants, pharmaceuticals. We could add things like microplastics now. It's a new pollutant, but excess nutrients can cause pollution, and it's a specific kind of pollution called eutrophication. So here's a picture of Earth showing nitrogen deposition. So the deposition of NO gases, or NO, both wet and dry, I think deposition, on the Earth's surface. And you can see that this deposition is highest in very high population centers, Eastern North America, Europe, parts of China, the middle parts of, well, I guess you wouldn't say those are really population centers in the Southern Hemisphere, but nitrogen deposition occurs because of both natural and human causes, but can be a source of pollution. Nitrous oxide is emitted during fossil fuel burning, and nitrous oxide measurements have been taken from ice core samples going back 10,000 years before present. This figure is a little bit misleading because today's value of over 320 would look more like this. Okay, so this graph is showing you a broken scale. So one way you can kind of hide data, but it's not a very helpful tool for showing the real change in nitrous oxide concentrations due to fossil fuel burning. When nitrogen is added, or nutrients are added to systems. You can take them from what are called oligotrophic, low in nutrients, to mesotrophic, higher in nutrients and productivity, to eutrophic systems, really overloaded with primary producers, algal growth, plants. But with productivity comes the productivity of other organisms too. So not all eutrophic systems are unhealthy. There's kind of a natural gradient of from oligotrophic to eutrophic lakes in particular. Here's a picture showing the Animas River in Colorado after a mining spill. So before the spill and after the spill. This was a devastating event and it had whole river consequences. And you can see that the average concentrations of certain elements, things like aluminum and sodium, are all really high. The minimum reporting limit, we're exceeding values for all things like barium, cadmium, calcium, higher for cobalt, chromium, copper, lead, manganese, molybdenum, nickel, potassium, selenium, vanadium, zinc. All of these things are coming from acid mine drainage and really mucking up the stream, the Animas River. Hydrofracking, so hydraulic fracturing, is this method of basically pumping proprietary liquids below ground, breaking apart rock layers to release natural gas. And unfortunately, as that happens, water sources become polluted, not just with the natural gases themselves. Here you can see a woman lighting her sink's water stream on fire. You can imagine this is not really good water for drinking or cooking or bathing or anything, right? So her drinking water source has been polluted. But additionally, the proprietary solutions of liquids that they pump below ground into the groundwater system are full of all kinds of things that they're not obligated to tell us legally because they're proprietary. So unfortunately, the pollution caused by hydrofracking is likely to be much worse than we even know. And then I'll just end with a couple more cycles. The sulfur cycle, you can see a lot is going on in the reducing side of the reactions, different kinds of sulfur transformations, lots of bacterial organisms working with sulfur in anoxic environments. You get the smell of rotten eggs, in anaerobic sediments where you have sulfur reactions taking place. And the iron cycle, this is maybe more involved. We have biological and abiological oxidation of iron. That's again rusting, changing from ferric to ferrous forms of iron. So anyway, there's a lot going on. There's a lot of chemistry involved in biogeochemistry, right? Biogeochemical cycling. And there's a lot to learn about how these ecosystems work. Okay, the last thing I'm going to talk about are some chemical factors in streams. So nutrients are really important, things like nitrogen and phosphorus. Of course, in streams, things like agriculture, fertilizer, septic tanks, phosphate detergents, and nitrogen-fixing organisms can all add too much nitrogen to a system. So Liebig's law of the minimum states that nutrients and resources can limit growth, but that and there's a lot of different nutrients that plants need. So they need hydrogen, carbon, oxygen, nitrogen, phosphorus, and then a bunch of micronutrients. Hydrogen they easily get in their water. Oxygen can sometimes be limiting, especially in aquatic ecosystems. And carbon comes in as either CO2 or their food. Okay. They also need things like nitrogen and phosphorus, so plants and microbes in particular. And basically this barrel represents all of the things that say a plant needs to grow. Each of the tines in the barrel represents a particular nutrient. You can think of it like a vitamin that you need to grow, right? Well, the factor that is found at the lowest concentration relative to the others will be the one that limits growth. So a plant, if you give it tons of nitrogen, that can be great, but at some point you're going to give it so much nitrogen that it's going to be limiting by phosphorus. And then you can keep adding nitrogen, it's not going to grow anymore because it's limited by phosphorus. And so I think of that as like a barrel with these tines that, one of these factors is going to limit growth. You won't be able to fill the bucket up anymore because there's not enough, in this case, potassium for the plant to grow. It doesn't matter if you add more nitrogen and phosphorus. It's not going to grow anymore because there's a limiting nutrient, and that would be potassium. Okay. So that's Liebig's law of the minimum. Another example is like you've got this automobile factory, okay, and you make a bunch of orders and you end up with 400 wheels, 800 tires, 50 axles, and 1,000 steering wheels. Well, how many cars can you build? Can you build 1,000 cars? You've got 1,000 steering wheels. That's great. But no, you can't build 1,000 cars because you only have 50 axles and every car needs 2 axles. So because you didn't order enough axles, you can only build 25 cars, even though you have 1,000 steering wheels. So it's a good example of a limiting nutrient. In this case, the limiting nutrient is the number of axles. Now, I just wanted to bring this up because a lot of these cycles, nutrient cycles, have anoxic and oxic parts. And so they have places where things like reduction and oxidation are going to be more common. And so here's the phosphorus cycle. And the details are not important necessarily, but just note that the brown parts of the cycle on the bottom have to occur in anoxic environments, and the blue parts have to occur where oxygen is available. And so some things need to take place where oxygen is available, and some need to take place where oxygen is not available. And each of the nutrient cycle figures that I'll show uses the same format. So here's the nitrogen cycle. Okay, so things like turning organic nitrogen into ammonium, that can happen in,